Sometimes you have a circuit which is not in AND or inverter form, right? So you're not going to end up with a simple sum of product expression like this circuit right here. It's going to be a little bit messy. I have a NAND gate here and an OR and an AND and a NOT gate. So let's go through it and see if we can come up with a Boolean expression for this. So into this NAND gate, I have an A and B. And of course, you know, a NAND gate is an AND gate with a NOT over it, right? Very important, I'm knotting the whole thing. It's different than just saying a NOT A and a NOT B. The bar goes over the whole thing. All right, so that is getting ORed with a C. So I have A, B, NANDed there, or that's plus C. And then it looks like in the end it's getting ANDed with a NOT B. So the whole thing, I'm putting parentheses around the whole thing, is getting ANDed with a NOT B. And that is a non-sum of product expression for this messy looking circuit. And we're not going to simplify it at this point, but you should be familiar with Boolean algebra and we'll review that. So that is my expression. Let's do just one more Boolean expression and then truth table for this non-sum of product circuit here. So let's say I just do this one gate at a time. This is a NOT gate, and so coming out of here I have a NOT C. So I'll just do a column for NOT C, as neat as I can. So I'm just inverting C, and that should be pretty easy. And I'm just breaking the circuit down one logic gate at a time. Maybe I'll do this AND gate next. So coming out of here I would have an A and a NOT C. So let's fill in that column, A and a NOT C. See, doing one gate at a time, now I just have to look at two previous columns. I just have to look at my A column and my NOT C column. And when they're both ones, I get a 1. So does that happen anywhere? They're both ones, I get a 1. Right there it happens, right? My A and my NOT C, and right there it happens. And everything else is a 0. All right, getting there. Have a couple more gates to go. Let's do this logic gate right here. This is a B ANDed with a NOT C NANDed, right? It's a NAND gate, so I'm ANDing it and then I have an extra NOT on top. But I'm going to do this in 2 steps. I'm actually going to do B ANDed with a NOT C, and then in the next column, I'm going to do the NAND part of it. So it's just a previous column, NANDed. So let's do the B, NOT C. I'm looking at every place a B is a 1 and NOT C is a 1. So that's once that happens, and a B and a NOT C, and that happens once more over there. Everything else is a 0. I hope I don't mess this up. And now I'm knotting that previous column, so I'm just filling in a 1 every place there was a 0. And 0 every place there's a 1. Okay, so I knotted the previous column. Just one more logic gate. So coming out of here, this is a NOR gate. So I have an A NOT C and a B NOT C knotted, but this is a NOR gate, so the entire thing needs to have a bar over it. Yeah, that's kind of a mess. That's the really big thick bar right there. Maybe I'll copy that expression. Maybe I can do it a little bit neater below here. So my final expression is that. All right, I'm going to do this in 2 steps. First, I'm going to do the A NOT C ORed with a B NOT C knotted, and let's see what that looks like. So that is my A NOT C, that's this guy, or this guy. Or means every time either one is a 1, I get a 1, right? That's a 1, so I get a 1. If either one of them is a 1, I get a 1. All right, what didn't happen there, but let's see, a 1, 1, 1. Wow, I guess I have a lot of 1s. All right, they seem to all be 1s except for one of them. Now my last column, of course, is just this guy, right? That's my, I guess I could have copied it again over there, but I'm not going to. So my final expression is just this previous column knotted. So every time I see a 1, I put in a 0, and yeah, I've got a lot of zeros there. So this is my final expression. And I hope you can follow that I'm really just breaking it down one logic gate at a time. And sometimes I use 2 columns even to complete a logic gate. And that is my final truth table for this circuit.